So today we're going to consider the question of gate. All right. The word gate, you can imagine it refers to kind of like how someone, especially someone with legs, moves. Okay. So like how your cat runs around, how your dog runs around, how the horse runs, and so on. Right. And is a useful how a human works, of course. It is useful word because it's sort of describes a something that is not so easy to organize for a robot. All right. Okay. You can imagine if you have a robot, you have to make a lot of decisions about how it's going to move. On some simplest level, you can say the decision will be how do we move the feet forward, where the feet are going to land, at which time they're going to land, what is going to be trajectory of the foot between landings, right? All those things, you can think of them as part of the gate, right? There will be a separate question of how to control the robot so it actually does what you planned for it. That I would argue is not part of the gate, but much more of a part of a control. Right? So today, gate. Okay. So first we will consider bipedal walking. That is not to kind of stray from our main focus, which is, you could say, mostly quadrupeds, right? Bipedal walking is very useful to consider because it provides us with intuition, which is completely transferred to quadrupeds, but without complexity, right? We can study bipedal walking, and then we get intuitions that we need for quadrupeds, right? Almost for free, right? Because we don't actually, when we go from bipeds to quadrupeds, we don't add more complexity in terms of this type of gait. So that is why we start with bipedal robots. Okay. Now, bipedal walking and running can be broken in phases, right? Phases. Those phases include, give me a second, I will just organize it. Okay. So those phases include double support, when 2 feet touch the ground, right? Single support, when only 1 foot touches the ground, and the flight phase, that is when neither of the 2 feet touch the ground. Okay. So running is defined as a gait where you have a flight phase. Right? So if you have a flight phase, it is a running. If at some point none of your feet touch the ground. Okay. Walking is defined as a gait which does not have a flight phase. Of course, you can talk about technicalities such as, you actually have to move forward for it to be walking, but technicalities aside, this is how it is. Notice I don't say anything about your feet, the way they contact the ground, right? That is a whole separate issue which we are not going to look much into in this course. But for example, you can mention if this is your supporting surface, your foot can touch the ground in many different ways. For example, it can touch the ground like this. If you can imagine, this is horrible. This what I draw makes me scared. All right, so I don't know if I can do better. Let me try to do better. Not highlighter. Vanishing pen, no? Okay. Imagine if your foot looks like this, right? And then the shin goes up. Right here, you touch the surface with your toe. That is, one kind that you can have. Another option is if your foot touches the ground in many places, right? With your toe, but also with your heel. And lastly, you could imagine if you if you touch the ground with your heel only, right? Different types of contact, is possible. And during human walking, all three are present. So if you're actually working with bipeds, it is likely you're going to worry about all three. But since our focus is on quadrupeds have point-like feet. They don't have heels, they don't have toes. So it doesn't actually matter all as much for us, like this problems of heels and toes. And since we don't have those problems, we don't have to discuss them in today's lecture. But for bipeds, just remember those problems would exist. Okay. Now, a simple model of walking would include only single support phase. Okay. So what I mean by that is we assume that while one foot is in the air, another stands on the ground. When the foot that was in the air touches the ground, another foot instantly goes up. This is a simplified model. Obviously, that is not how bipedal robots walk. If you imagine how you walk, when your heel strikes the ground, usually when you walk, it is your heel that first goes into the ground. Your toes, your other foot would still stand probably on the toes, and your toes are still on the ground. And it is only when your heel is firmly planted, then your toes would actually lift off. Makes sense. But for us, here again, we don't think about heel and toe. So we would consider this simplified model where as soon as one foot lands, another lifts. So at no point both feet are in the air. At no point both feet are on the ground. Okay, so simplified model. Simplified models are going to be the whole point of today and next day's lecture. So it's very important. Okay. Now, single support phase of walking, so this whole idea, can be characterized by step length, right? So how far are you going to step? Like, what is the distance that you are stepping over? Okay. A time allocated for a single step. That is also interesting idea. And velocity of the center of mass. That is, if your velocity of the center of mass is, you can say, is constant, for example, if it is constant, which is again simplification, of course. But if it is constant, it would sort of identify a relation between this value and this value, right? Because if you know the step length and you know velocity of the center of mass, you could compute how much time it is allocated to perform the step, right? Center of mass and the stepping over large periods of time would have to correspond to each other. They don't have to correspond instantly, but over large periods of time, they have to correspond. So you would be able to compute one of those two given another, and if you know the velocity of the center of mass. And of course, position of the next support, place where you land, it depends on the position of the previous support. You could say plus the step length, roughly speaking. Okay. Please notice that all of those are verbal constructions. Those are not mathematical entities. Step length, how do you define it? Do you define it from the previous foot to the next foot? Do you define it from the center of mass to the next foot, to the next position of support? Velocity of the center of mass, do you define it as average or do you define it as instantaneous? Time allocated for a single step, do you define it as in from between the same foot lifts up to the next moment when it lifts up, or do you define it between when left foot lifts up and or right foot lifts up? There are many ways to define all those, and ultimately it's not very important how you define them. What is important is once you define them, you have to stick to your definition carefully. So Okay. Now, for double support walking, so if you actually had a phase where both of your feet were standing on the ground, you would additionally have a duration of the double support phase, right? That is just to say that if you actually had this, which is very characteristic for bipedal robots, you would have additional characteristic here. But that's it. During the double support phase, nothing much changes except the position of the center of mass. So it's quite easy to add this parameter. It's not going to be a completely revolutionary change. Okay. Now, we can identify two popular approaches to generating gaits. Okay. There are many. I'm only mentioning two popular ones. Okay. One is Rybert style approach. Rybert, here is Mark Rybert, is the person who in the 80s, late 80s, early 90s was famous for his work on jumping robots, robots that were able to jump around. They were kind of, you can say walking robots, but they were more like jumping robots. They were jumping on 2 feet. But they were moving forward the way, you can imagine, like they were doing gaits, basically. They weren't just jumping in place, okay? Then he founded Boston Dynamics, which in the early 2000s was famous for his Big Dog robot. That was a completely, you could say, a revolutionary in terms of capability robot. It was extremely impressive. And now it is, I think, mostly famous for Atlas, which in 2014, unless I'm mistaken, was performing really great on DRC, Dark Robotics Challenge. Was made history, you can say, there, where 6 teams were able to use the same robot to successfully compete. It didn't win. I believe a team with a different robot won. If I remember correctly, it was Kaist, Korean team. But the robot was quite impressive. And after that, quite recently, probably you have been experiencing this, they created 2 revolutionary types of robots. One was Atlas, named the same as the previous one, confusing, yes, which was able to dance, do somersaults, jump around. If you have seen bipedal robots on YouTube, chances are you have seen new model of Atlas, okay? Those have not been widely available as far as I can tell. Mostly I have seen them being developed inside Boston Dynamics, but maybe something changed since then. And another one is Spot, which is a quadruped robot, which was very well designed. At the same time as Spot, there appeared 2 other robots, Animal from Any Robotics and Uni3 A1. And this last one was extremely cheap. And this started this last 3 years of constant revolutionary growth of quadruped robots. Quadruped robots weren't big just a few years ago. They started to grow so fast because the price went down significantly. And the models of those robots, you can trace them to many different sources, but one of those sources is Boston Dynamics. Though arguably there are maybe even more important contributors. All right, so Rybert is this guy, one of the fathers of the field. And the Rybert style approach is we decide on the desired center of mass velocity, right? So we have center of mass of the robot. It has some kind of desired velocity. And from this information, we compute step length, okay? So we compute step length from this information. This approach allows us to be dynamic. We could, using this approach, be take advantage of dynamical properties of the robot. We can easily do running or increase our speed significantly and so on. This is the approach that tends to human-like gaits, if you want. Okay, so like jumpy gaits, you can say. And the second one is the MP style approach. The MP style approach is what used to be popular in the 2000s. That approach you can associate with the robot Asimo, if you remember. It was a robot designed by Honda. One of the first successful bipeds, maybe the first successful biped, you can say. Very famous robot. And the characteristic of the MP style approach is that the robot is not going to fall down if you use the MP style approach. It's going to be very slow, energy inefficient, but on its own, it's not going to fall down. It's very stable. That is why bipedal robots like this approach. Even during their robotic challenge, as far as I can tell, most robots used the MP or the MP-like approaches. Because for bipedal robots, falling down is extremely dangerous. They break. Whereas quadrupeds, they almost never break and hard to fall down when you have 4 legs. Right, so the MP style approach is we decide a sequence of footholds. So we decide where we put our feet. You see the difference instantly, right? Here we were deciding velocity, and then we compute where we put our feet. Here we decide a sequence of footholds, so where we are going to put our feet. And from this, we compute center of mass trajectory. So first, we decide where we're going to put our feet. Next, we compute the trajectory of the center of mass from this. So 2 different approaches. We are going to focus on this approach here. Like in this lecture, we're going to focus on this. This approach is suitable for quadrupeds, and quadrupeds right now use this approach, right? Bipeds, for them, the MP is still useful, and a lot of bipeds that are successful have been using the MP approach. So Boston Dynamics bipeds, which are jumping and dancing around, clearly they don't. So this approach, I feel like maybe is going away, but is has been crucial for development of bipedal robots. Right. Now, to understand this hybrid style approach, we have to consider inverted pendulum. Okay, so let us just spend a little bit of time looking at it, and then we can understand better what the approach is all about. So inverted pendulum is governed by these dynamics. Here I ignore any source of dissipation of energy. So this model assumes that the energy will remain constant. Here, I guess I should maybe mention what those are. Inertia, mass, length, gravity, angle that describes the position of the pendulum. Okay. Right. Now, kinetic energy and potential energy of the system can be described like this. Kinetic energy is inertia times velocity squared divided by 2. Potential energy is length times gravitational force. Yes, this is basically mass times g is, of course, g gravitational acceleration, so together it's gravitational force. Right? So this mass times length times gravitational force multiplied by y minus sinus phi. Right? Okay. Now, assuming that there is no dissipation of energy and no actuation, so there is no actuator attached to the pendulum, the total energy remains constant. So the total energy is conserved and is given by the sum of these pluses and remains constant. Okay. Very important observation here. So energy remains constant. Okay. Now, let us model a single support working as inverted pendulum moving from time t1 when the angle of the robot phi of t1 is equal to alpha to the time t2 when the angle is equal to phi of t2 beta. Okay? So it working a robot will be modeled as inverted pendulum. You can think of yourself as a pendulum, right? It's like your mass is above the ground and you stand on, if your foot is point-like, imagine if you stand on your toes or on your heel is even better. You kind of like a pendulum, right? So imagine we model the walking like this. Single support, so means only one leg, right, on the ground. Everything else is in the air. Your center of mass moves kind of like this pendulum. So that's what we are going to model the robot as, okay, as a pendulum. And the angle at the beginning of the phase is alpha, and the end of the phase, it is beta, okay? Good. Now, potential energy at the beginning of the single support phase is equal to 1 minus sinus alpha lmg. Angular velocity is omega 1. Okay. W1, which is omega 1. Omega 1. Okay. At the end of the single support phase, it is P2, which is equal to 1 minus sinus beta lmg, and angular velocity is omega 2. Right. So this allows us to write total energy in the beginning of the single support phase. It is j omega 1 squared divided by 1 plus 1 minus alpha lmg, and which is equal to the energy at the end, because energy is conserved. At the end, it is j omega 2, 1 minus sine beta lmg. Okay, now let me observe that we have this component, which is the same on the left and on the right, so it cancels out. Without it, we have minus alpha, minus beta on the both sides. We can move them to the left-hand side. Okay. So this we can move here. Beta becomes plus, right? And LMG, we divide everything by LMG. Okay. And this we keep. So I just rewritten the same equation. Now let us consider what I wrote here. Let's consider what I wrote here. Let me see if I have a slide. Yeah, I have a slide. So now I reverse what I wrote, like divided by itself, you can say. Sorry. What I do is I express V1 minus V2, okay? The relation between those two. Previous was like relation between angles. This is the relation between V1 and V2. Let's understand what it is. So this difference is equal to this difference multiplied by a positive constant, okay? Same as, the other way around. If we, like difference between angles would be equal to the difference between angular velocities multiplied by a positive constant. It's just the constant is inverted in two cases. Okay. But let's not worry about that too much. It's like this constant is, just a positive constant. Okay. All right. Now, on the left-hand side, what we have is two squares and the difference between them. On the right-hand side, we have two trig functions, sines, and the difference between them. Okay. Sine for any angle which is less than 90 degrees positive. So both of those are difference between two positive numbers. Okay. Now, if beta by absolute value is equal to alpha by absolute value, this would mean that sine beta equal to sine alpha, and this becomes zero. Therefore, this becomes zero. So omega 1 equals to omega 2. It means that if in the beginning of the support phase and at the end of the support phase, the angle phi of your pendulum is the same, if it is the same in the beginning and at the end, your angular velocity is not going to change. We will look in the illustration in a second. But importantly, by absolute value, it doesn't have to be, the sign can change. That's fine. Okay. Now, if the angle at the end is bigger than angle at the beginning, then what we will have is this is, if this angle is bigger than this angle, right? What would this thing be? Let me just double check that I don't say anything stupid. I sort of feel like there is a typo. Let me just double check. Is there a typo? If beta is bigger than alpha, then sine beta would be bigger than sine alpha, right? Yeah. Now sine beta would be bigger than sine alpha, right? I don't make a mistake here, right? I don't think so. Yeah, I don't make a mistake. Then this would be a positive number, and that means that this guy would have to be bigger than this guy. So omega 2 would be bigger than omega 1. Okay. All right. And vice versa. If beta is less than alpha, then this would be a negative number, and this would have to be bigger than this. So what is important here is that there is a clear relation between the angle at the beginning of the support phase and the angle at the end of the support phase, which would influences the difference in angular velocity in the beginning and at the end. All right. So if we want to increase angular velocity, we know a relation between the angle at the beginning and at the end that we want to have, right? Same if we want to decrease energy, we also know what to do, okay? So this relation comes straight from the conservation of energy. Right, now let's look at the illustration. Hopefully next slide is illustration. Yes, okay. Okay, now here's your inverted pendulum, okay? Here's the mass. This is the rod on which the pendulum rotates. Here's the point of contact. Here's your angle in the beginning. Here's your angle at the end. Okay. Now what happens is your pendulum rotates from this position to this position, right? It just rotates like this. And initially the angle looks like this. Then the angle looks like this. Okay, right. Okay, What we want to think about when we look at this is the following. What happens when the robot starts like this, right? So it has some, the other foot is in the air. So you can imagine the other foot is maybe something like this, just in the air. It doesn't touch the ground, so it doesn't matter. We consider that the foot is irrelevant here. This is the foot that touches the ground. You can think of it as, like this, for example. Okay. As we move, we have initial velocity, right? So we have velocity when we start. The velocity points this way. Like there is only one way velocity can point here, like it is this way. Because if the rod is rigid, it cannot have this component. Like this component is impossible because the rod is rigid. So a velocity has to point this way, right? As the pendulum approaches this position, right? The kinetic energy increases. It means that potential energy increases. It means kinetic energy will decrease, right? This is the maximum potential energy in this position. And then potential energy will decrease all the way until here, okay? At this point, potential energy will be low, maybe lower than in the beginning. It depends on beta angle, right? If beta angle is bigger than alpha, then potential energy would have decreased more, right? Okay. All right. So what we can from this conclude is, since energy doesn't dissipate, if at the end of the phase the body is kind of lower, closer to the ground, it means kinetic energy increased compared to what it was in the beginning. If the body is higher than it was at the beginning of the motion, then the kinetic energy would have decreased over the course of single support phase. So we have a situation where we could predict if the kinetic energy overall decreased or increased. Okay. I think it is quite easy to, I think it's easy to see that this is going to happen, right? Easy to see that this is going to happen. And so far, so good. It's okay. We can imagine also what's going to happen next, right? What's going to happen next? So suppose this body arrived at this end position. Then we can say, okay, let us have this alpha angle again reserved here, right? So let's say we have the angle of attack of our foot, like this angle of inclination of the foot, be the same as in the beginning. Then we get this new position for the point of contact, which is going to be here, right? It used to be here, now it is here. And now we have our new point of contact, and then our body can move again in this direction, right? Notice that the velocity of the body instantaneously changes direction of motion. Like it was going this way, right? And now it instantaneously goes this way, okay? So this is a little bit strange about this model. You can imagine the collision with the ground instantaneously changes the velocity of the center of mass. This may look strange to you, but in fact, if you can imagine that's what we call a rimless wheel. Rimless wheel, that is like a wheel which doesn't have a rim. It has spokes, like one. I don't know if you're familiar with those terms. spokes are what you have in the bicycle that keeps your tires attached, right? And all this kind of stuff. Okay. If you imagine a rimless wheel, you can construct it, like you can make it out of wood, for example, or metal. So it would have spokes, it wouldn't have a tire, only spokes, but rigid spokes, okay? If you kick it, it's going to roll around, you know? Of course, the energy will dissipate, but it will roll around. It's not going to, you know, behave in some alien way. It's going to be, roughly speaking, a wheel, okay? So it's going to work, no problem. And this wheel is essentially exactly what's going on here. As soon it stands on one spoke, kind of like a pendulum, right? At some point, it lands, like this part will land on the ground. This part will land on the ground. And then the velocity of the center of mass will change from being like this to being like this. Instantaneously will change. Same as here. The impact collision will do this. So it's not a nonsense. It's not a mathematical joke of some kind. It is just a description of how actual physical object would behave. Okay. All right. All right. So you can imagine this whole picture. The picture is fine, is interesting. You know, we could reason about if it's going to be faster in the beginning or faster at the end, right? Purely from energy. Nice. Let's move on. Let's see how we can apply it. So what this pendulum model indicates is that if we want to increase kinetic energy, we need to decrease the angle alpha. Right? If we fix beta, so I mean, when I say decrease more alpha, of course there are many ways to do it. I'm just indicating one way. Okay? So if we fix beta, so if beta is not allowed to change, then we decrease alpha, and this means shorter step length. Let's look at it. So let's say this is constant. This is constant. It means that this distance, like from here to here, is constant. But alpha can be decreased, right? And alpha corresponds to this distance. Okay. Alpha corresponds to this distance. And if alpha decreases, the total step length decreases. Okay. All right. So if we want to decrease kinetic energy, we need to increase the angle alpha. Right? So if we fix beta, and the pendulum is in the second quadrant, right? Then this corresponds to a longer step length. Okay. All right. Now let's look one more time at this picture, but now with legs. So as I said, here is our step, which is depends basically on like alpha and beta. This part remains constant because we fixed beta. This part depends on alpha. Okay. Now, what happens if we decrease alpha? Well, our step kind of go like instead of being like this, kind of goes maybe like this. Right? So your kind of body leans forward more. Okay. Okay. what happens if we increase alpha? Then your step maybe goes like this a little bit. So your body leans back more. Okay. Let me see if I have an illustration. A second. Yes. Okay. You can imagine when a person accelerates. That's actually kind of what they do. The center of mass leans forward a little bit. Let me see what color would actually show. I think blue maybe will show. Right. So the center of mass moves forward a little bit. Right. And this foot is very bent. Okay. While this foot is very straight. Like you can see, there is this, like the difference between the foot as like a line. The foot itself is very small. So it's like, how should I put? What you can say is, if you're going to model it as as a pendulum, this foot actually looks like is longer, okay, than this. That's how you can say it. Okay, that's how you can say it. We will look into it in a second, right? But this foot is kind of straightened, and this one is bent quite significantly. And the center of mass kind of leans forward. And I didn't prepare this picture, but you can imagine if you're going to decelerate, if you're going to slow down, you're going to actually run kind of like this, and you're going to put your feet in front of you to quickly decelerate, right? And when you walk normally, you don't have either leaning forward or leaning backwards. Your steps are, roughly speaking, kind of like even. So this model makes sense in terms of our experience. It's not completely crazy. Okay, now let's move back a second and consider this question about the length of the feet. So if somehow this angle alpha, let me use a smaller size font, just one second. Can I actually make a font a small size? Yes. If this alpha is the same as this alpha, okay, but this height is less than this height, right? That's what we said, remember? We said that the height is going to decrease. That is why we have increase of kinetic energy. But if the alpha is the same, but the height is less, that would mean that this distance is less, right? Visually, I think it is very clear that this is true. So the size of your foot decreased over, or of your pendulum, if you want, decreased, a foot, I say leg, okay, sorry about that, decreased over a single supporting phase. So next time, your pendulum will be shorter. Okay, that is the problem. Your pendulum will be shorter next cycle. Not good, not good. And this happens because we, fixed up. We could have avoided it by not fixing alpha, but that is not what we want. In fact, we want this decrease. Why do we want this decrease? Because it provides us with this bent foot. Okay. In fact, if I drew it more carefully, what we would see is let me increase the size like this and like this. If I draw it very carefully, what I would have is maybe something like this here, right? This very bent foot, and maybe something like this here, like very straight foot, kind of like what we saw with the runner. Our next step would be on a bent foot, which we could then unbend, right? we could push ourselves up a little bit. So during the running, we could, like as humans, for example, we could make this leg elongate because we just unbend the knee. Okay, so everything here is fine. We don't actually need to fix this situation with the shorter foot. The situation with the shorter foot indicates that the knee is bent. That is perfectly fine. Okay. Now, let's now say the same thing, but in a more careful way. So, since total energy of the system is the same, right? It remains. That means if kinetic energy at the end of the phase increased, potential energy decreased, right? Of course. It implies that the center of mass is lowered. So at the end of the phase, center of mass is lower than at the beginning of the phase. So given a constant alpha, it would imply a shorter leg, as I was saying. Now, the way we could solve this problem is by introducing a spring into the robot leg. So a spring which would actually push us up while we walk. And not just spring, but a loaded spring. So a spring which is preloaded. So during the walking, it would kind of go up. The deformation of the spring is related to the change of the leg length. Stiffness is a hyperparameter. So it is a parameter that you can tune to get your gait correct. Okay. So the idea is normal, right? During walking with positive acceleration, we bend our legs at the knee, but this leg would straighten quite fast, right? You put your leg bent and then you straighten it up. Okay. Right. So the way this model looks like is like this. So we have what we call a flight phase, which I'm not sure if I'm super happy about the picture or about how it looks, because this sort of suggests that this guy flies, that lands, does this whole stuff here, and then flies again, which is how you would model this. It's actually, you have animations of those. So if you look at YouTube, you would find those springs kind of jumping like this. It's very pretty looking. What I don't like is that this doesn't visually correspond to how you imagine walking. Okay, it's a little bit confusing, I think. But if you think back to our pendulum, I think it starts to make perfect sense. Let's consider it starting here. Okay, here's our leg. Here we step on the leg, right? Here we lift the leg. Okay. So far, so good. So far, so good. And let's say we then perform our change of contact position. So let's say next contact position is here, right? So at the next point, we could have a preloaded spring. Okay, so the leg is shorter. We can have a preloaded spring. And the spring will push us out, right? It will push us out. And what we will have is basically this description of a knee unbending, but not in terms of a knee, so a tooling robot, but in terms of a spring, right? Just a spring that pushes us outwards. Why flight phase? Well, you can think about it this way. As soon as the spring, kind of like, how should I put it? As soon as the spring reached its zero extension position, After that, it doesn't start pulling on us. It doesn't start like when the body kind of like is ready to take off, the spring no longer tries to keep it. It just allows it to go off. It just allows you to go kind of like leave the ground. This is to prevent the effect where your foot can somehow stick to the ground and keep your body, keep your body in contact with the environment. It doesn't work. Instead, your spring only works for unbending your knee, but nothing else. It cannot do anything else but unbend your knee. That's it. It's just, you could say, like a way to describe a spring, which is one-way spring. It only pushes you, it doesn't pull on you. That is the flight phase. That's like how you can make sense of it, right? But also another way to make sense of it is just to say, okay, forget about pendulum, consider this guy. We will only use the pendulum model to ascertain the angle alpha here. Nothing else is of interest. You can say angle maybe here, like those angles may be of interest, but they kind of come out from the model. Like at some point, the body will leave the ground, and that will be, that will be your angle. The only angles that you need as a hyperparameter is the angle here, which during the flight phase, it can be anything, so you have to decide on it. Like every other angle is actually comes out of simulation, right? So there are two ways to think about it. One way is to think that we fixed linear inverted pendulum by adding a spring which unbends our knee and prevents this shortening of a leg. And the second way to think about it is we just simulate this jumper, whichever you prefer. Okay, as you will see soon, it's not really important. It feels important to decide on all of this, but for Rabbit-like controller, it's not very important. So if this sounds confusing, don't worry. Of course, it is. It can be important if you're actually going to use it for something. It's just that you don't have to. Is a useful thing, of course. Is a useful thing. Okay. Here's basically a paper which you can, if you want, look up for description. Okay. Same as previous paper ones. Sorry for all those detours, but same as previous ones. Like this model, all of them have quite a literature around them. So it's not so easy to point out just one paper. This, for example, is not a paper that introduced this. It's just a paper where I took this image from, and it's one of many papers where this is discussed. Okay, now finally we are ready to hear what Rabbit style planner is. Okay, now finally we can do it. Okay, so a Rabbit style footstep planner is works like this. So assuming forward motion, so we do not change orientation, we only move forward. Okay, we can propose a formula for computing the next step allocation. Okay? And for that, we take allocation of the next step would be equal to allocation of the center of mass, current location of center of mass. Okay. Then we add to it this, which is a vector coming from the center of mass to the robot shoulder. Okay. So if you have a robot, let's say quadruped, because at this point it doesn't matter if it is biped or quadruped. Okay. So here's your center of mass. And you can have, for example, this length. Right? this length, that would be RC, RS, right? Like distance from the center of mass to the robot shoulder, okay? Then separately, you have this guy, which is the velocity of the center of mass times step time, like step duration, you can say, okay? So those are so far very sensible. Current location of center of mass, okay, this guy, plus the distance from there to the shoulder, okay, makes sense. Plus the velocity of the center of mass times the time, right? So it kind of means you would put your step, let's say you go in 1 meter per second, and your step duration is 1 second. So it means step 1 meter forward, okay? But now you have this final component, which is the most important one, this guy. That is K, so Rybert gain, times the difference between the current velocity and the desired velocity. So if current velocity is higher, this would be negative, and this guy would be smaller. If current velocity is bigger, this would be positive, and this guy would be bigger, right? Okay, so this is the strange part. Before I address it, let me just point out maybe the obvious. Like, for example, what is delta t? Right? What is delta t? Like, how do you define this distance to the from the center of mass to the shoulder? All of this, I feel like, is like hyperparameters, basically, that you need to carefully tune for your robot. It doesn't make sense to try to memorize them. Instead, you just need to see that when you're actually doing for a robot, you need to make sure that what you do makes sense, okay? So I don't know how you would define the step time. Maybe for you, the step time is the time between the next, like, between your feet starting to move, each time between the foot starting to move, right? That would be like the whole step phase. Maybe you define it in some other way. Maybe you define it as the time between any two sequential feet moving. That would be half the phase of the walking. Maybe you define it some other way. I don't know. It's up to you, right? And if you try to memorize a definition that I give, but your definition for the time is somehow different in your code, that's just going to be a problem. So instead of doing that, just use common sense. Okay, like you understand what this does. It compensates for the distance your center of mass travels during your step. So, use this when you are implementing this formula. So that's where you get your delta t. Okay, all right. Now, let's consider the effects. So if desired velocity is bigger than actual velocity, this component is negative, right? This is bigger than this. So the steps become shorter, as I said. If desired velocity is less than actual one, then it is positive, and the steps are longer. If they're equal, then the steps remain the same. So this component does not influence the steps. Notice that this corresponds exactly to what we did before. So fixing better, shorter step corresponds to smaller alpha. So more kinetic energy. And the longer step corresponds to larger alpha, right? So that would mean less kinetic energy, right? So basically, you can think that a Rybert controller, what it does, it looks at this way to pump kinetic energy into the system, which you do by making shorter steps. So you stop running like the guy on the picture. Okay, this is what you do to increase your velocity. Okay, increase your kinetic energy. And yeah, and of course, you can also argue that since you have some friction that drains your energy, you constantly need to replenish it. So this is not only for acceleration, maybe in a sense, this is also for maintaining your velocity. Okay. And if you want to decrease kinetic energy, you need to run the way a person would run if they try to slow down, right? That's it. That is the motivation behind Rybert's controller. But the way it looks is quite simple, right? You account for current position of center of mass. You account for geometry of your robot. You account for how much you're going to travel at the current rate. And then you add a little bit to for the dynamics to increase your velocity or to decrease your velocity to the desired one. This is how modern robots actually work. This is extremely popular, is being done across the field. So it's very easy to find this type of controller. Okay, so this is a paper which people cite when they discuss this type of controller, right? Is Rybert, C. Mark Rybert and his co-authors, right? You can see that it is for one-legged hopping machine. So as I said, all of this started with hopping robots, okay? Hoppers. Okay. Now, what we covered so far answers one very simple question. How do you plan where you put your foot next time, right? Like you know where you put your foot currently, where do you put your foot next time? That is what it answers. Now, what it doesn't answer is how do we control the robot so it actually does this? And this is what we are going to answer next. And we're again going to use simplified models. Today we used simplified model called SLIP, spring-loaded inverted pendulum. And this, which is, we call it LIP, linear inverted pendulum. Okay. Next time we are going to use what people sometimes call potato model. So potato model next time. Yeah, which would allow us to do model predictive control. Finally, you know, we spent so much time working towards model predictive control. Next time we actually can do it. Yeah, and both this and model predictive control would give us access to the paper by Kim. It's from MIT, which basically lays out traditional modern design for quadruped robot controllers. Right. I think that's it for today's lecture. I'll stop the recording and you can ask questions if you have any.